Hi everyone. So today for the webinar, we are very happy to have Professor Tamer Başar. So Tamer Başar is a professor of electrical and computer engineering at the University of Illinois Urbana-Champaign. He has made many contributions to optimal control, in particular robust control, and dynamic game theory, estimation theory, and other topics. And he's a member of several scientific organizations, including the National Academy of Engineering and the American Academy of Arts and Sciences. Thank you very much for accepting to give a talk today about mean field games and learning. And so we are looking forward to your talk. Thank you very much.
Okay, thank you, Matthew, for the invitation, and welcome to everyone who have connected. And I don't see your faces or even your names because of the way the system is. But it's a pleasure to give this talk. It's going to be an overview talk, and one thing I just noticed is that I have as the year 20223 here, which it was too late to change this. The talk is not going to be that futuristic. I can tell you in advance. So this is going to be, as I said, an overview talk, and I'll talk about mean field games and talk about robustness issues that can be introduced into computation of equilibria, and then some learning aspects. But that's even though the webinar has both mean field games and machine learning, I won't be spending much time on the machine learning part. That would have been a separate talk. So here's the outline of my presentation today. I'll first give a high-level introduction to non-zero-sum stochastic differential or dynamic games. Differential when the game is defined over continuous time, and the dynamic if it's defined on a discrete time interval. And I'll talk about strategic interactions between players, which is what makes games so different from single agent optimization problems. And there the information structures play a role. Who knows what and how much is shared. And there is no complete theory for that with a finite number of players. And this is one of the reasons why we go in the limit to an infinite number of players. Certain difficulties can be overcome, difficulties that arise in the finite population regime. And so I'll give a quick introduction to the mean field approach and why it's so relevant to stochastic differential games as well as difference games. And then we'll introduce two different types of robustness. One is through risk sensitivity, the other one through sort of adversarial input into the system dynamics. And I will, for special types of games, which will be linear quadratic ones, because we can obtain explicit results there, which will be of consensus type. I'll look into two problems. One is risk sensitivity approach to robustness. The other one is the adversarial input approach, and then draw the parallels between them and what the differences are. And then we'll, after making the connections between P1 and P2 between these two problems, I'll introduce the epsilon Nash equilibrium and obtain, for the finite population game, some approximate solutions. And then as time allows, I'll talk about some extensions to multi-population models as well as learning. And then we'll conclude. So game theory provides definitely the right modeling and computational framework to capture interactions among multiple interacting agents or players or actors. And so these are used interchangeably. And these could be physical, economic, social, or even biological. And these players or agents have misaligned objectives. And if they are totally misaligned, and if you have only two agents, then you have the zero-sum framework. If they are partially misaligned, and particularly if you have more than two agents or two players, then we have the framework of non-zero-sum games. Now, this was game theory, and the initial work has been on static game theory, and then through extensive forms, researchers have looked into dynamic games, and motivated by developments in control theory, then differential games have started to enter into this research landscape. And dynamic game theory definitely provides a much richer framework, which captures the evolution of the interactions between agents over time, and how much information they gain along this during the evolution of the game. Who knows what and when? There could be memory restrictions. That's something which doesn't arise in static games, but in dynamic games. How much of the past occurrences, past events, can agents remember? And that creates difficulty. If there are memory restrictions, then that leads to difficulties in the computation as well as in characterization of equilibria. There could be resource constraints, and how can resources, budget constraints, for example, how can they be allocated over time and utilized over time? And then there could be short-term goals and long-term goals, and then the trade-offs between these. So none of these actually arise in static games. So that's why dynamic game theory provides a much richer landscape. And we have multiple solution concepts. Nash equilibrium, there is Stackelberg equilibrium when you have a decision hierarchy among the players. There is a Markov perfect equilibrium, which corresponds to sort of subgame perfectness in games, and when you have access to perfect state information. And these are all tailored to the scenario at hand and the roles of different players in the decision-making process. As I said, if it's a symmetric decision-making, then you have the Nash equilibrium. If it's hierarchical, you have a Stackelberg equilibrium, or you could have a combination of the two. Now, when you have an infinite population of players, the interactions among these players take a different meaning, and that leads to mean field games. And the associated solution concept is one of mean field equilibrium, as I'll clarify shortly. So let me give you in the continuous time a sort of a general description of a non-zero sum stochastic differential game. You have let's say that we have n players, and you have a state equation which is inputted, which has as input the controls or the actions. In game theory, it's more called action. In the context of control theory, U is a control variable, and then you have a Brownian motion here, which drives the system. So this is a general sort of stochastic differential equation. Now, generally in applications, we have a partition. The state equation comes in partition form, where each agent has a local dynamics. That's what the I here stands for the ith agent. And they interact, not all agents may interact with each other through the state equation. Some of the interactions could, in fact, be through the cost functions or loss functions, as we'll see shortly. And so in this case, in partition form, you have the differential equation, again, another stochastic differential equation, for which is essentially a decomposition of this one, and which has as input the action of the ith player, and then has as input some quantity which depends on the actions of other players, maybe a subset of them, and also the states of the other players, and maybe again a subset of them. And it could. This is generally something which comes in as an aggregate quantity in most applications, and definitely in mean fields. For example, the CI dependence on the states of other agents could be the average of the states of other agents that are in the neighborhood of the ith agent. So a neighborhood could come into play, which is here I denoted by script ni. And likewise, the actions of other agents should come to enter through an aggregate quantity, which could be the average of the actions of all agents in the neighborhood. Okay, so this is quite a rich framework. Now, as I indicated at the beginning, that we have quite a what differentiates dynamic games from static games is the importance of information structures. And so there's a difference between an action and a policy. The policy picked by an agent will lead to an action. Implementation of the policy will lead to an action. So let's denote the control policy for player I by gamma sub I, which lives in some space. I'm not going to specify what that space is, but in a precise formulation of the game, this will have to be specified. Generally, one takes it, puts no restrictions, and takes it as a general Borel measurable function from the information available to the action space. Now, one important information structure is closed loop perfect state for all players. And so what that means is that a player, the ith player, has access to the state of all players. Okay, so this would be asking too much, especially if you have a high population of players. But at least if you have a two-player game, then this may be a reasonable thing. And the other one is the local state, which is much more something that arises in applications more frequently. And this is the one where each agent can observe only his own state, and also has full memory. In other words, remembers what the values of that state have been in the past. Of course, this does not decouple the agents completely, because the state of an agent will depend on the actions of other agents, at least in the neighborhood, as well as on the states of other agents. But that agent is not able to observe these states, which makes the derivation of, say, Nash equilibrium extremely difficult in these problems. And then there is the measurement feedback, where you have a noisy sort of access to the state of the agent, his own state, as well as maybe of other agents. I mean, you don't, if this doesn't appear here, x minus I, then it means that you just have a channel which provides for the agent I, which provides noisy state information of his own state. And again, this is a Brownian motion which drives this measurement process. Okay, so therefore the HI could be, depending on the application, could involve just XIT here, or the excess of other agents in the neighborhood. Okay, so now to complete the formulation, we need a loss function for player I, and the loss function will generally be compatible with the partitioning that I had above, and so therefore I haven't really used that partitioning here. And the cost function is this: the continuous time problem is an integral of some cost of the state and the control and action. Again, this could depend only on the state of that particular agent and the control of that particular agent, or states and controls of other agents in the neighborhood. And then there's the terminal cost. So this is a finite horizon problem. You can also introduce an infinite horizon problem where generally you take the average over capital T after you divide it by T. And so you take the expectation, of course, these are all random quantities. You take the expectation when the controller is implemented through a policy. And so therefore, this is what's called the normal form of the game, which is defined on the policy space. So now you strip away all the information structure is already embedded in the gamma, in the definition of the gamma, and there is no stochasticity here. And so then what we would be looking is a Nash equilibrium here when with the start quantities that if all players stick to their sort of policies as dictated by this n tuple, then the ith policy cannot do, ith player cannot do any better than picking gamma I star. So now, if I mentioned Stackelberg equilibria at the beginning, also as another possibility when there is a hierarchy in decision-making process. So let's bring in what I would call a zeroth player, who would be called the leader, and the others are called followers. And the followers, the n followers, actually play a Nash game among themselves, but they play a Stackelberg game with the leader. So again, you have a stochastic differential equation, which now I have introduced, added another action variable by the leader. And again, this could be in a partition form. The leader's state equation could depend on the state of the leader, the state of the action of the leader, and some aggregate quantity which depends on the actions and the states of the followers. And then again, driven by a Brownian motion, and this is similar to what I had earlier. And the only difference is that there is a U0 which has entered here, and which is very important because it's through this term that the leader would influence the evolution of the dynamics of the followers. Now you can have a loss function for each player, and now the player I goes from 0 to n, and you take expectations, and you again have a game in normal form. Now, the Stackelberg equilibrium here is, so as I indicated, the leader announces a policy, and then the followers, here we have n followers, they respond to it by playing a Nash game. Now, the solution of that Nash game may not be unique. Let's assume that there exists a solution, actually. But it may not be unique. So the question is, how does the leader has to come back and pick a policy gamma 0 star, which is most favorable to him, given the responses, Nash equilibrium responses of the followers. And but if that response is unique, then it's clear. Then your the function that the leader will have to minimize will be a function of his own policy, and also a function of the responses of others, which will be unique if there is a unique response, which will depend on gamma 0 also. So both of these terms will depend on them. Now, if the reaction set is not unique, then the most reasonable solution concept would be one where the leader would pick the worst element out of this and do an optimization subject to that. And now there are other types of definitions in case of non-uniqueness in the literature. One of them, the other extreme, would be the most optimistic one, where instead of sup here, you have an inf. And but the assumption there is that the followers who are non-cooperative players are in fact cooperating with the leader in picking the most favorable Nash equilibrium among all, which may not be that reasonable. So this is a sort of a guaranteeing, this is a pessimistic sort of equilibrium solution concept, but it guarantees a certain level of performance for the leader. And so there are many challenges in deriving Nash equilibrium and Stackelberg equilibrium. And I'm sure most of you are familiar with my book with Gert and Olser, and going back to the early 80s, actually, and this is the latest, the SIAM version. And where there's we make a clear distinction between different information structures and the difficulties that arise in the computation of Nash equilibrium. And so if there is close to perfect state information, then you can have a recursive computation. It's essentially dynamic parallel running of dynamic programming equations, which will be coupled. So there again, the existence uniqueness would not be that straightforward, but at least one has a set of sufficient conditions for equilibria. And with open loop information, one uses the maximum principle in that case. And now, for the Stackelberg equilibrium, when the leader has open loop information, note that the open loop information means that the leader knows only the initial state and does not have access to the states of the other agents. So if it doesn't have access to the states of the other agents, then it means that any policy that the leader picks is not going to be a function of the actions of other agents. So that makes the computation of the reaction function much easier. And whereas if the leader's policy had involved closed loop perfect state information or closed loop information in general, which would bring in dependence on the actions of other players, followers, then that becomes a much more complicated problem, and then it has connections to mechanism design and so on. So that would be a different talk if I had to go in that direction. Now, so this is what I say here in the second bullet, that any information structure other than closed loop perfect state and open loop for Nash equilibria and open loop for the leader, but it could be closed loop for the followers. Anything outside that is extremely difficult, and there's no general theory. For example, if you have local state information, even in the deterministic case, even if you don't have a noisy channel, decentralized measurement feedback and so on, there's no general theory. So solutions, generally, if they exist, they would be infinite dimensional, even for finite dimensional problems, even in linear quadratic problems. Now, why is this so, and where does the difficulty come from? I sort of alluded to it briefly in the context of the first bullet, but the reason is the strategic interaction among the agents. And each player, even if you have a two-player game where the players do not share their measurements, and but the measurement of let's say that player A and player B, the measurement that player B has access to, if it were shared with player A, then the player A would end up with a better performance. So therefore, the player A, from what he observes, will have to guess what the information the other player it received and what kind of information and what the nature of that information is. And this is not possible in a static game, but it's possible in a dynamic game. the second guessing, because the game evolves. And this second guessing, why I call the second guess, because if player A second guesses player B, then player B will have to second guess player A, and player A also has to double second guess what player B was second guessing about player A. So that is an infinite recursion, and it leads to some asymptotic sort of derivation, and things get as you iterate, then the dimension of your space grows, and so this is almost intractable. So it is. So one runs into these problems if there is what we call asymmetric information among the players. Now, just to remind you, most of you, I'm sure, know this. For the linear quadratic non-zero sum stochastic differential games, if there is perfect state information by the agent, they share everything, all the state, and then the solution, as I indicated, you have a dynamic programming equation, coupled equation. One can show as in standard LQG control or LQR that the value functions are quadratic, and they can be computed offline through Riccati equations, and the problem then boils down to essentially existence of a solution, a uniqueness of a solution to these coupled Riccati equations, and there is a lot of work in the literature that analyzes this in different contexts. But so in this case, the situation is very clear. Nash equilibrium is linear in the state, and the conditions for existence and uniqueness are essentially boiled down to existence of unique solutions to coupled Riccati equations. Now, when information is local state or imperfect state measurement, even if it's shared by all players, existence and characterization is an open problem. And now the question is there any hope of solving problems of that type when you have local state information, when n is sufficiently large? And the answer is provided by mean field games. And so there is when we talk about mean field games, or the not really mean field games, but an infinite population of players, there is an insightful statement that one can find in this book by von Neumann and Morgenstern, which is known as or recognized to be the starting point of game theory research. So they say in their book, this is on page just 13 and 14, when the number of participants, they talk about the difficulty. I mean, not the kinds of difficulties I talked about here, but the kinds of difficulties that arises with some sort of strategic interaction among the players. They say when the number of participants becomes really great, some hope emerges that the influence of every particular participant will become negligible, and that the above difficulties may recede, and the more conventional theory becomes possible. And it's a well-known phenomenon in many branches of the exact and physical sciences that very great numbers are often easier to handle than those of medium size. This is, of course, due to the excellent possibility of applying the law of statistics and probabilities in the first case, and the strong law of large numbers, for example, in the case of mean field games, comes into play. So essentially, what this says is that if you have a very large number of players, what a single player does, and when we are talking about non-cooperative decision making, players act independently. Without any collusion, without any cooperation among themselves, and what a single player does not have has only an infinitesimal impact on the outcome of the game. And so therefore, each player will have to look at the aggregate and what that aggregate means. And by the law of strong law of large numbers, that aggregate for some classes of problems of interest to us and to the community, it leads to a deterministic sort of a process. And so therefore, all these things about strategic interactions among different players, the second guessing and so on, disappears, and arises the hope that one can obtain Nash equilibria even for games where the information structure is only local to a player. So here is the mean field game formulation of what I had earlier, the stochastic differential equation for agent I. So I don't have any leader here. I'm talking about just the symmetric roles by the players. And so this is you'll remember that I had this function C here. And so I'm replacing C with xn, which is the average of the states of all the agents. Now, if n is large, whether you include the ith agent here or not does not make any difference. And but the important thing is that in each agent's local dynamics, the other states enter through this term. Now, it's possible to enter the average of the other actions as well, or to do the summation over a neighborhood, assuming that the neighborhoods are large, they have high population. So those would be extensions, and they go to this model. But let's keep it at this simpler model. And the cost function for agent I in this n-player game is one where it depends for the ith player, it depends only on the local state of that player and the action of that player and that aggregate quantity, xn. So the general approach in mean field games is that you treat this xn as a fixed stochastic process. Let's call this the mean field. This is called the mean field term. Let's call it Fn, which is the mass behavior of all the agents, not affected by agent I's choice of control. And again, when n is large, that's definitely the case. And so what does that do? This essentially decouples the games for different players. And so what each player faces, what in this case the ith player faces, note that this is now a stochastic process which is not correlated with xit. And so therefore what you have is a stochastic state equation, the differential equation, which is driven by Brownian motion and which has as input another stochastic process, which is at this point fixed, and likewise in the cost function. So this is a stochastic control problem, and we know how to solve these stochastic control problems. And this is the state equation becomes what's called the Makin-Vlasov equation. Now you obtain the solution, the control U, and you do it for every player, and then you generate the state process, and then you come back and compute xn. And but note that the solution, the control, was a function of xn, of this stochastic process. And now you come back and compute xn, which in terms is going to be a function of xn. So you end up with a fixed point equation. And then the problem boils down to solving that fixed point equation, whether it has a unique solution or not, and many results have been obtained in that context for different types of problems. And then once you solve it, let's say that there is a unique solution to that fixed point equation, so which means there's a unique xn, and in the infinite horizon case. In the infinite population case, that is as n goes to infinity, and now you apply it to the and then you have the control, which is a function. Note that the control is going to be a function of the, when you solve the stochastic control problem, is going to be a function of xi. So that's the dynamic part. And it's also going to be a function of this stochastic process, which can be computed offline. And so therefore, the control uses only local state information, which was not possible when we treat this as a finite population game. Okay, there's no theory for that. But if you go to the mean field limit, then the solution that pops out very naturally is one that depends on the local state of that player. Okay, then, but our interest is in a finite population game, and so therefore we say, how good is that policy that we have obtained using this mean field game approach? How good is that for the finite population game? Of course, we cannot expect it to be a good approximation if there's only a few players, 2 or 3 players. But if n is sufficiently large, then we may expect some, because of some continuity results and so on, the solution to be quite close to the Nash equilibrium of that finite horizon game. So that's what one studies, and for finite n, comparing the two, and this leads to an epsilon Nash equilibrium. And in a specific example, I'm going to talk about this. And so this research was initiated by, as you all know, by Laszlo Lyons, and from a different angle, from a PDE point of view, and by Juan Keynes and Malhame, which appeared in the Transactions of Augmented Control, both in 2007. And so what are the computational aspects of this mean field approach? So the first thing, which is very appealing, is that the mean field equilibrium-based approximate Nash equilibrium policy is scalable. It could scale up to any number of players. And the computation involves, as I indicated, the solution of a fixed point equation. But to be able to solve the fixed point equation, you need a full modeling knowledge. In other words, a separate person, a separate individual or a machine will have to collect that information, full model, to have access to full models and then solve that fixed point equation. Now, how can we get around that in maybe a recursive way? And there are several research efforts trying to sort of reduce the computational effort in this characterization of the fixed point. One way would be for each agent to interact with the central coordinator. The central coordinator would give an average value for the states. Each agent solves his stochastic control problem, finds out what the trajectory is, and then sends it to the central coordinator. And the central coordinator and then recomputes the average and then sends it to all the agents, and so on. And this actually would converge, and there are many results on this. And if you have different populations of agents, and then you have to compute L different mean fields in that case, and I'll, as I have time, I'll discuss some of that. And so not only so that you can even apply this sort of recursive technique with when there is not a single mean field equilibrium, but there are multiple mean field equilibria, or there are multiple mean fields when you have different populations, different types of agents in each population. And what if the agents do not know their own models? Then this brings in reinforcement learning for each agent into the iterative learning process. And the recent reference on learning-based computation, what I have in this third bullet is in this paper, which just recently appeared in Dynamic Games and Applications. And at the very end, I will talk a little bit on this or summarize on one slide. Okay, so there are many applications of mean field games. So there is the stochastic Kuramoto model. There is the stochastic Cocker-Smale dynamics. I'm not going to spend much time on these. Temperature dynamics for energy efficient buildings, and many other diverse applications in social networks. For example, the recent interest is in the spread of epidemics and disinformation. Definitely, there are many agents involved in this, so the mean field approach would be a very natural one. The smart grid, demand response management, communication networks, application bandwidth allocation, cloud computing is in serverless function as a service platform, financial markets, transportation networks, and even in molecular biology. So there are many papers which address these applications within the mean field thing. Now, let me talk just a little bit about robustness, because I promised that I would touch on robustness also. And so there are two approaches to achieve robustness. One is with sensitivity, the other one is adversarial input, and they are connected. So what does risk sensitive formulation does? You take your loss function and then you exponentiate it. So you exponentiate it so that when you do a minimization of this expected value of this, then you are emphasizing more sample paths which are less favorable to the individual than others, than the more favorable ones. And this parameter delta actually determines how much emphasis you put on unfavorable paths and how much on the favorable paths. So delta is a positive quantity, and this is the so-called risk sensitivity parameter. Now, some people would be risk-taking, in which case the delta could be negative. And so this is, you take the logarithm, this is a monotonic transformation, of course, and this is your new J, the new normal form of the game. And you can define the Nash equilibrium as before, and the same difficulties with regard to information structures and strategic interactions as before. Now, the other approach is you take the state equation and you add an adversarial input to it, and that adversarial input is controlled by another player. Either each local information, each local state is affected by an independent adversary, or the same adversarial input is injected into both. So depending on which model you adopt, you either have a new n+1 player game or a 2n player game. The n players are the original Nash players, and then you have each one has is being countered by an adversary. So that's why you increase it to 2n. And so for the infinite horizon case, more specifically, this would be the formulation. So now I'm going to discuss the risk sensitive one and the one where we have adversarial input, and then see what connections we have and how we can solve these problems in the linear quadratic setting. So here is a linear quadratic state. Here's a linear state equation. Again, the local state equation, which is affected by only the ith player's action variable, and theta I is the type of that player, and then you have the Brownian motion here, and this is just a scalar quantity which will play some role in the development. And then you take the exponential of this quantity, which is the standard sort of integral of a cost function, of a local cost function. And note that here the state equation does not involve the states of other agents. So this is for simplicity here in this exposition. So the way the agents are uh, connected and or coupled is through the state equation, through the cost function. And note that this is like a consensus term. Each player wants his state to be as close to the average of the states of all agents as possible. And then this is a cost on the effort of that agent. Okay. Now the risk sensitive control, it's the robust control with respect to this risk parameter delta. That delta you can play with to make it more robust or less robust, or more pessimistic or less pessimistic. Now, if you expand this in terms of delta, then what you have, the first term is the risk neutral one. In other words, you are just minimizing the expected value of this. The next term is the variance of y, which is multiplied by 1/2 delta. So the risk sensitivity parameter comes in here, and the rest is in the order of 1/2 delta. So what does for small values of 1/2 delta or large values of delta? The risk sensitive approach looks at a linear combination of the mean value of phi and the variance of phi. There are results where, and this is a different approach, where you put a constraint on the variance, so that would be variance constraint problem, and then you minimize the expected value based on that constraint. And so let's call this as FNT, which is the mean field term, the mass behavior. Now, as I indicated, the agents are coupled with each other through the mean field. So what you do is you replace this by FNT, and what you have to solve is a risk-sensitive stochastic control problem, and which has a robustness built into it. And then you have to go for the fixed point. So that's going to be the approach that we'll be taking. But first, let me introduce the second problem, which is one where you have the same state equation, but there is an additional input here. This is the adversarial input. And here I'm taking the view that there is a different adversary, or even if it's the same adversary, that adversary controls independently these different state equations for different players. Okay, so the VI is going to be picked by the adversary depending on the local state, and so therefore the worst case, and this is a risk neutral one, but it's a worst case because of the VI. And so what we are looking for is the J in this case is simply the supremum, if there's a maximum, it's the maximum over all policies of the adversary, ith policy of the adversary of the expected value of this. And this is 1 over t because we're looking at the infinite horizon. And here the cost function is still the same, but there is an additional term which tames the adversary. This is you have to put some constraint on the effort level of the adversary, and the gamma parameter, which will have a relationship with the delta that I had earlier, will have a role to play here. So if gamma is too small, then that would mean that the adversary has too much freedom, and then it could drive this to very high values or even to infinite. And in the linear quadratic context, it could be driven to infinite. So there's going to be some constraint on gamma. Gamma has to be larger than a certain value gamma star, which can be pre-computed actually, and so that the problem will make sense. So you cannot give total freedom to the adversary. You have to put some effort on the adversary, and this corresponds to this in the risk-sensitive case, the delta parameter. And so, as I said, VI can be viewed as a fictitious player of agent I who strives for a worst-case cost function for agent I. And the agents are, again, it's a consensus problem. The same, exactly the first part, the first 2 terms are exactly the same as the SP1. Okay. So, as I discussed earlier, what you do is for each fixed mean field, let's call it by G, and in the infinite population case, you have a stochastic control problem. But in this case, this is these problems are difficult than the ones that are different from the ones that I had introduced earlier, because the first one involves the minimization of a risk-sensitive cost function, not a risk-neutral one, and the second one involves minimization of the supremum of this over the adversary's controls, or it involves the solution of a zero-sum game. Okay, so this one is a stochastic control problem, P1, for each fixed G, and the second one is a zero-sum game where the players are U and V. U is minimizing, V is maximizing, and subject to, and note that this X here is the for player I, it is the ith player's X. So this is the generic player here. So you essentially you have a G of T. You do each player solves a stochastic control or a zero-sum game, and then computes what comes out of that is a G, and then you iterate, okay, and find out, either solve it as a solution of a fixed point, as I have here, or you do it through iteration. Now, if this map tau here, or T, is a contraction mapping, then when you start with an arbitrary G and then you iterate, then you are going to converge to the true mean field in this case. Okay, so very quickly, what are the solutions to these control problems and the zero-sum game? It turns out that they are the same, and with some difference in the mean field itself. So this is the solution of the problems faced by a generic agent in both P1 and P2. And the generic agent in one case, again, faces a risk-sensitive control problem. In the other case, a zero-sum game. But the solution is the same. And the solution is given by this. And the solution is characterized by gamma and the relationship between gamma and delta and mu was what multiplied the Brownian motion, is given by this expression. So there is the gamma is intimately related to delta if mu is fixed. So if you have a stabilizability of AB, standard condition, and detectability of AQ and a F, then we have a unique solution. This is the generalized algebraic Riccati equation, generalized because of this term. And it does not have a solution for all values of gamma. Gamma has to be larger than a certain critical value, and this arises in H infinity optimal control as well. And then you have the Hurwitz, the closed loop matrices are Hurwitz. But note that in the two problems, even though the solution is the same, the closed loop system matrices are different. Why? Because in one case, it is just the resistor. There is no adversary. This is the case without adversary. Whereas here there is adversary, and there is the input of this adversary, which is this, which enters into this problem. Okay, so this is the part that depends on X of t. And one can show that S has a unique solution in the space of continuous and bounded functions, and is given in this form in terms of G. So the it's not a pure feedback. It has another driving term in the controller, and the reason is because it's a target tracking problem. I mean, you can view this as a target tracking problem where X of the state of a generic agent is tracking the average states of all other agents, which are actually captured by G. So the two robust tracking problems are identical, and this is related to, as I mentioned, robust H infinity control problem with respect to gamma. But what about the mean field solutions? Is the G the same? So for P2, let's change it to H. And so therefore, these are the fixed points. One is the mappings are different in the two problems, because one is a zero-sum game, the other one is a risk-sensitive control problem, and so the mappings are different. In both cases, you can prove that there is a contraction condition that applies, and then you have a unique solution. But are the fixed points the same? And well, I'll go quickly through this. You can use the strong law of large numbers, which you can show applies here. And these are the contraction conditions for the two problems. And the conditions are different. And in both cases, they are G star and H star in the two problems are best estimates of Fn. And the G star is not the same as H star. So the mean fields are different, even though the controls are the same. And when gamma goes to infinity, note that gamma was the weight on the effort level of the maximizer in the zero-sum game. If gamma goes to infinity, and gamma, of course, is related to delta, so which means that you are optimistic in a sense in the risk-sensitive framework, then the risk-sensitive control problem is the same as the standard risk-neutral control problem, stochastic control problem, and the zero-sum game essentially cancels out the adversary, because the adversary's effort level is infinite. So then the two problems are the same, and one can actually show that G star is the same as H star in this case. Okay, now I mentioned earlier that, well, you obtain the solution to the mean field problem, but how does it, what if I want to apply it to a finite population game. And do we have any level of approximation that we can prove? And indeed you can. And if you have the uniform, you have to. I had that theta in the which captured the different types of agents. If we have a uniform agent case, that's you have an interval where theta lies and agents are uniformly distributed over it, then one can show that the error, we have the mean field solution provides an epsilon Nash equilibrium for a finite population game, and it is in the order of, the epsilon is in the order of 1 over square root of n. Okay, but the important thing here is that this epsilon Nash strategy is decentralized. That is, it's a function of x sub I and g star, but g star does not depend on the other x's. Whereas if I were given the finite population game and I had focused on it and wanted to obtain the Nash equilibrium, there is no theory for that. As I indicated, there is all the second guessing and so on. So this way one can obtain at least an approximate solution to some degree for a problem which otherwise would not have been solvable, okay, for which we do not have any. And the lower, the question is, how close is this G star to the average of the xi's? And one can actually show that through the law of large numbers. As n goes to infinity, this actually goes to 0. For all t, almost surely, for all finite t. And also, as t goes to infinity on the average side, the average time, it also goes to 0 almost surely. And G star turns out to be a deterministic function in this case, not a stochastic process, and can be computed offline. And the same type of convergence holds for the other game for P2 and there with the which I had denoted by H. Okay, so we have a partial equivalence and limiting behaviors of P1 and P2, and again, as I indicated, as gamma goes to infinity, both of these problems lead to the linear quadratic mean field game, and so they are equivalent. And there is only a partial equivalence between the two when gamma is finite, and this partial equivalence is equivalence in the sense of the control itself, but not in the sense of the mean field trajectory. And so limiting behaviors, again, as mu, and you can let the mu and delta go to 0 at some rate and still keep gamma to be positive. This leads to a small deviation, small noise limit, and the same results hold under this limit. And the risk neutral, as I indicated here, the G star is the same as H star. I'm not going to go through the simulations. I'm running out of time because I want to mention one other result. But here, like theta I is an IID uniform random variable on the interval 2, 5. And in this case, one can compute that gamma star just to give you an idea of what gamma looks like. Gamma star turns out to be 1. So you have to work with a value for gamma which is larger than 1. So we have done simulations using gamma 1.5 and 150. And the G star, H star can be computed, and you can see that they are different. Both the these multiplying constants, and the exponential itself is, the exponent is 8.49t minus here minus 3.37. Okay, so, and then the epsilon 2, we have results on which show simulations which show how this converges to 0 as n goes to infinity. So I'm going to skip this. So extensions, what if there are, here I talked about the single population, and what if there are multiple populations, and each with a cluster of different types of agents, and with an underlying network topology? What if players do not have access to the full model? How can they compute the mean field? Perhaps by interacting with the central simulator, as I discussed earlier. So this is essentially, I mentioned this paper, so this is, I don't, this would have been a different, a separate talk, but just give you a little bit of a taste of the kind of problem that has been looked at, and at a high level what the results were. And so you have different populations, L populations, and the L population has n sub L agents in it. Later, L is going to remain finite, the number of populations, but the n sub L is going to go to infinity. We are going to have a high population in each, high number of agents in each population. And each agent has a linear. So I have switched to discrete time here. That's because the paper deals with discrete time problem. And so you have the discrete time state dynamics for agent L, for agent N in population L. And then you have a zero mean Gaussian sequence, IID. And each agent has only local information, does not have, and this is again a consensus type of problem, but there is also dissensus there. So agents have intra-population as well as interpopulation couplings in the cost functions. So the couplings come through the cost functions. And note that here, this is the cost function of the nth agent in the Lth population. Each agent has wants to minimize his state, norm on the state and the effort level, but also wants to keep to have x as close to the mean value of x in his own population. So wants to be close to others. This happens in opinion dynamics. You want to be close to the opinions of others whom you favor, who are in your neighborhood, in a sense, but the neighborhood is defined in terms of closeness. But then there are others in other populations, and you want to stay away from them. And so therefore, when you pick X and L, again, the nth agent in the L population wants to stay away from the average of the other the agents in the other populations. And there is, by how much, this is the beta parameter that is picked. So you want to be close to beta plus this, so which means you want to be sufficiently away from this from these agents. So this is the dissensus term, and this is the consensus term, and let me just share with you the main results there. Each agent again solves the taking the mean field approach, solves a stochastic control or tracking problem with the mean fields of the L populations taken as exogenous processes. Okay, so here you cannot take, this is the mean field of the self population for agent N in the L population, mean field coming from the L population. And this is the mean field coming from other populations. And so therefore, if you have capital L different populations, you have capital L different mean fields or exogenous processes. So you do a tracking problem, and then under standard assumptions of controllability and observability, one can show that there exists a mean field equilibrium where the control of each agent, generic agent, is affine in her local state information. And there are offset terms there. They appear because the beta is positive. And the mean field for each population is generated by an affine system. And now, if you bring in the single population game, which I discussed earlier, we have an epsilon Nash equilibrium. In other words, if you implement the mean field equilibrium, mean field control to the finite population problem, then you have an error in the order of 1 over n. Now here we have multiple populations, so how does that extend to this framework? It turns out that a generic agent of population L, when the mean field solution is implemented, ends up with a Nash equilibrium, an approximate Nash equilibrium, where epsilon is in the order of 1 over the minimum of the size of the neighboring populations. Okay, so what governs this is the minimum. If one of the populations in our neighborhood is very small, then the approximation is not going to be good. But if they're all going to be of about the same size or high, then the approximation will be very good. Okay, and if the agents do not have full modeling information and do not even know their own dynamics and cost functions, but only have access to noise estimates of their cost, then one approach is to learn the mean field equilibrium. One approach to learn the mean field equilibrium is to use reinforcement learning and interact with a central simulator, as I discussed earlier. And generally, these problems, when you use the reinforcement learning, is when you have multiple agents. So this is the multi-agent reinforcement learning. It is a very difficult problem because the environment is non-stationary from each agent's point of view, and the non-stationarity coming from the actions of other agents, and you don't know what those actions are. So the affine structure of this problem and allows us, in this, as discussed in this paper, to decompose the RL algorithm into two parts. First, one can learn the linear part and then the offset part, so we can get over that non-stationarity issue. And then the paper also discusses zero-order stochastic optimization tool used for the reinforcement learning, and one can obtain finite sample guarantees for both parts of this RL algorithm. Okay, so what I have covered is the benefits of going from finite to infinite populations and then back to finite, to circumvent the complexity of dealing with strategic interactions and the difficulty created by decentralized information, and the decentralized policies which are adapted to decentralized information, or particularly local information, come out very naturally as a result of this approach. And I have discussed how robustness could be incorporated into designs to two different but connected means. Multiple populations, just the last few slides, can be built into the mean field gain models and discuss their analysis. and also some computational, very briefly, and learning aspects of obtaining the mean field equilibrium. What I have not covered is hierarchical decision structures like stackable equilibria, incentive designs within the mean field game framework requiring totally different sets of tools and different approaches. And again, with dynamic information for the leader, this is an extremely difficult problem to solve if you have a finite number of followers, and so therefore you have to go to the infinite limit. And we have results on general discrete time mean field games. Here I discussed just the linear quadratic and what we can obtain explicitly in that context. And so we have in several papers, actually 4 papers, which have appeared, discrete time mean field games, both with imperfect state measurements as well as perfect state measurements, and with discounted cost, as well as with risk-sensitive criteria in these papers. So the last sort of statement I'll leave you with is that this area of multi-layer network mean field games with learning, robustness, and incentive designs is quite a fertile ground for research, and we're going to definitely see many developments in the coming months and years, and this is a very fruitful area of research, particularly for the younger researchers. It's something to invest in, and in terms of your time. Okay, thank you.
Thank you very much for the very nice talk. Are there some questions from the audience? Feel free to unmute yourself if you want to ask a question. Otherwise, I have one quick question about the robustness part. So you use the model where you have some mean reversion, attraction towards the mean, if I remember correctly. Is it something crucial for the kind of equivalence you obtain between P1 and P2, or do you think it can, like in principle, it could be extended to other mean field models, maybe linear quadratic?
It could be extended. Actually, one can show, first of all, for general stochastic control problems, the two are essentially equivalent. The two approaches. I mean, I have papers for even nonlinear systems. You can write down the Hamilton-Jacobi-Bellman equation for the stochastic control, and write down the Isaacs equation for the zero-sum game, and show that the solutions are the same for stochastic control problems. For mean fields, yes, you can go. You can show that you can extend beyond the linear quadratic framework, specific framework that I have.
Okay, sounds good. Thank you very much. More questions?
People can write to me, of course, if you are interested in any of the papers and other questions. Feel free.
Okay, thank you. And if you don't mind sharing the slides, I can also upload them together with the recording.
Yeah, sure.
Okay. Well, thank you again for the very nice talk. Thank you so much.
Thanks, Matthew.